Okay. We still have quite some material to cover. And it's now getting a bit more concrete, remaining in the space of not algorithm specific, but the approach that you should take in if you approach some machine learning problems are often very similar. So in this way, I really like this approach from Peter, whose slide I've taken over here, to present you really a recipe for dealing with problems. And basically, this is choose the features. And this sounds very simple, but it's very powerful, as I hope to show you today. Choose the model class. This is something for which you need a lot of information, and you need to look into the algorithm, the models, and so forth, what you can predict, and so forth. And then choose a method to find the best model within your model space. And that's basically, as we are going to see tomorrow, a search problem again. So I think today, most of the time will be spent on the features. And then I hope I'll have some time for simple Bayesian classification, because I really like it as a very simple tool and algorithm. And a little bit of time for the ML project, hopefully, and maybe I will ask Peter to explain the AlphaGo algorithm in more detail on Wednesday. So let's go. Let's get some terminology straight. I've already used some of those terms. We look at, in this case, a classification problem where you have the age of a person and the height of a person, and you want to classify whether it's a male or a female. And you usually do that by, we're looking at here numeric values for your features. That also works for non-numeric values, but in all the examples, we just look at a numeric feature space for the sake of making it slightly simpler. And basically what I'm going to talk about is the sort of the feature vector as a vector of the individual values of the attribute pairs. So the feature vector for this individual here would have a value 7 for the age on their first position and a value 119. And then it would be assigned to a class, in this case, the male class, the blue class. And when we have this representation, we can easily think of this in terms of a feature space, so a mathematical space, where each of the features are on the x and y axis, and the vectors then represented by a point in this feature space, and the classification would be a color scheme assigned to each of the points in the vector space. And this obviously works easily for two dimensions. So if you have a vector space of a feature space of 2 attributes, then we can easily and nicely show this. This also works in a one-dimensional space, where you only have values here, and then you would somehow look into this and search through this feature space. It also works graphically a little bit for 3-dimensional spaces, and then it becomes a bit more difficult. But the principles are always the same. So you have your feature vector and your representation of a vector as a point in the space. Yeah? So we stick with the 2-dimensional case in most of the examples, and only sometimes tomorrow, I believe, we also get to 3-dimensional, which generalize a little bit. And now the task is, of course, depending on what kind of task we're looking for, can we somehow find out which part of the feature space belongs to the red and to the blue ones. So the inductive learning is here, that in this feature space that we have to make some decisions. We can either draw a line to classify, but now let's start with a regression problem. So the idea is that we have some training data, and we want to find now a function f that predicts the value for a previously unseen value of x. That's the definition of the regression problem here. And now the task is, how can we come up with an interesting function that can help us for this prediction? There are notions of consistency when it agrees with all the examples that we have. And the task comes down to fitting of a line to predict. So this would be a linear regression algorithm that tries to find a linear function that predicts the values of f of x given given x. But obviously this is sort of an arbitrary choice that we choose here, the model of a line. We could also choose a model of a hyperbole or whatever this is. So, and if you see, then this more complicated model fits those data points better than the line. Still, none of the two really is good enough to cover this one. So this new model class that we would now choose, not a simple hyperbole, but sort of a free function, I would say, is very good on our training data, but the question is how really would it perform on real data? Oh, we have something like this, which would also be consistent with all our training data sets. So this is also this one would also count as a consistent curve fitted to this data set. But obviously this isn't, we wouldn't expect this to work well if we only have those points to start with. We wouldn't expect it to work well on unknown data because we have nothing to suggest that this point should be up here. So I go here directly. So the question of model fitting is to find the right model class for a certain problem. And if we look at our points, we've seen already that, okay, the line might have many errors still, but it's very simple, and it might be good for prediction of new elements, maybe better than the very complex one at the end, even though the latter one was consistent with the data and the first one not. So it's exactly this task of coming up with a simple model class that fits our problem and our data. And there is one sort of very old principle that guided, I think, machine learning in the last 50 years, and that's the principle of Occam's razor, where you say one should not increase beyond what's necessary the number of entities required to explain anything. The idea of making your explanation or your model for prediction as simple as possible is what came out of this suggestion from the Middle Ages. So when many solutions are available for a problem, then choose the simplest one. Then the question is, what is simple? In our case, the function is relatively simple. And sometimes you can evaluate the quality of your model class with a priori knowledge and so forth. But it's very important to remember that for a very simple problem such as this one, just to come up with a function, a regression function for this kind of data set, you can have different types of functions, namely lines or hyperboles or whatever. And you need to make a decision up front which one is the best one for the representation of your problem and the data that you have. So in this sense, everything you do in machine learning starts out with the bias on finding a representation, finding the right model for your prediction. And that makes this linear classifier so appealing. It's very interesting, very intuitive, it's very easy, it's mathematically very easy. And that is just basically coming up with a line in your feature space and yeah, use this one as prediction for your either classification or regression problem. I will now give one example of such an algorithm. And tomorrow I will look more into the question of can we maybe do something with the feature space rather than the model class that helps us separate the positive and the negative examples? So that's, I think, a very nice trick of dealing with the feature set. For now, let's just understand it or keep it very simple. We need to come up with some kind of model, like classifier, like a line in this case, to help us make the decision. And I want to give you now a very simple algorithm, and that is based on the probability theory from Friday for Bayesian classification. So it's sort of more a tool that you should apply. We have again the same situation. We have a feature set. We have we have training examples, so it's a supervised algorithm, and we target, in this case, in this simple example, we target the simple problem of spam filtering and see how that works. So our task for now is to come up with an algorithm that makes this distinction between the two classes of something being spam, in this case the right one, or being a proper email to someone. And of course, we have to make the decision of what are the features in this case in order to represent this problem as a feature space in this feature space representation. So the setup is I get the emails and so forth, and the features are what you get in principle for free. So the words in the email and maybe some more information about dollar symbols or caps and so forth. We're just keeping it to the words here to keep it very simple. And if I say I want to represent this in probability, then basically the problem that we have here is that there is some uncertainty about, given some words in our data set, whether something is spam or not. Yeah? And what we want to make a decision upon is whether the probability that something, given those words in the email, is spam or not. And we want to maximize so that the probability that something is, if the probability is higher that it's spam, under the condition that we have those words in the text, then the probability that it's not spam, then it should be returned as spam. So basically, this is what we want to do. We want to calculate the probability of something being spam, given a set of features, where each of the features is just a word in the text. Yeah?
Everything is spam from the beginning, just figures out what is spam.
That could be, yeah, but what?
Just like
the problem will be the same. So yeah. It's just so that you need the. What do you mean by the other way around? I don't get the.
It's like you always say it tries to figure out what is spam, but like it tries to figure out what is ham.
Oh yeah, okay. But the problem in principle, you want to estimate the probability whether something is ham on the basis of some information about the document. So that's the features here. So what's the problem with calculating this probability? So this is the conditional probability of given a number of words in this case, features, whether something is spam or not spam. Yeah?
It's not the probability of each feature that it's a spam or not a spam.
Say the first sentence.
It's a probability of each feature knowing that it's a spam or not a spam.
This is what we're going to do. So you're already know the solution to the problem.
I thought we were going to do the probability of it being a spam knowing that we have these features.
Yeah. So given that we have the words, we want to calculate the probability that it is ham or whatever.
But if we compute the Bayesian probability, we get the opposite.
Exactly. So this is something that's very difficult to estimate because we would need to have seen a very similar email before with all the words and know whether it is spam or ham. But this has never happened because all the way of writing spam emails is far higher than we can have a check. And that's where the power of the Bayesian classifier comes into. Then we can use Bayes' theorem for now turning this around, because we have very many examples of something that is a spam filter, that is spam or ham. And now we can use, in our training sets, of all the things that we have identified as spam or ham, we can identify features. So basically, this is exactly one of the points where the power of the Bayes' theorem comes in, that we discussed on Thursday. Namely, that we can calculate this probability by just the probability of something being ham or spam, and the probability of given something previously identified as ham or spam, what are the probability that certain words occur in it? Which is something we can do because we have a collection of data sets that have been, where the emails have been specified as ham or spam.
So,
yeah?
Does that mean that you, for example, F1 to Fn, that's a vector of words, and you're comparing that to previous knowledge? So if those, like the high probability of those words are almost 1, you say it's spam again?
Yeah.
Okay. Just a question.
So, and then you have to normalize it by the probability of a certain word occurring. So if you have a word that occurs is very rare in your collection, but it only occurs in spam, then the chance is higher that this is indicative for spam. Yeah. So that's great news because in principle we have a collection of previously trained emails. And we know the features in them because we have the words, and we can calculate these probabilities and these probabilities and these probabilities. So we can simply calculate probability where this is spam and probability where this is ham for any input of features F1 to Fn. There is a problem with that, and that is basically that if you look at Bayes' theorem, we have on the right-hand side this factor, and that is that given a class C, how do we calculate the probability of F1 to Fn being the case? And this is basically rewritten through the product rule, or the chaining rule, sorry, into the probability that C happens, multiplied by the probability that C happens, that under the assumption that C happens, F1 happens, and the probability of under the assumption that F1 happens and C happens, F2, and so forth and so forth and so forth. So we need to calculate all those values, and that is far too expensive to calculate if we have a huge data set. So what has been said instead is that we assume conditional independence between the features in an email. So this is an assumption where I just say every word occurs with the same, with no dependence on any other word in the text, which is obviously not true. So New York will be, the two words New and York will very often occur together. So basically, if we wanted to calculate the probability of a term like New York occurring in spam or ham, we would have to calculate it the proper way. But the interesting thing is that in these naive Bayesian approaches, as it's called, you just assume this independence, and it's still a very powerful algorithm. So instead of calculating this complicated probability, we just say we assume the conditional independence, and that basically means that we can simply multiply all the individual conditional probabilities in order to estimate the true probability. There was one more thing that I've skipped, and that is, remember that we want to estimate the probability of something being ham or spam. So we want to know whether this one is bigger for C equals ham or C equals spam. Yeah? We want to know which one is the bigger, which probability. And if you now look at the denominator down here, you see it's independent. It doesn't depend on C. It's just the probability that a number of words occurred in a text. So as this is independent of C, it is the same for hem, and it's the same for spam. So basically, it doesn't make a difference in the decision whether the one is higher than the other. So what you can then do is simply, in the calculation of the probability, you can A, apply the naivety assumption that you do the conditional independence between the features, and you can leave the denominator. And then the question of calculating the probability or approximating the probability for something to be in a class A or in a class B is simply to max, given a set of features f1 to fn, take the maximum, so which one is higher, the one for spam or the one for ham, for the prior probability of the class C itself, and the multiplication of all the conditions for this specific class. And this is now very simple and very cheap to calculate. So basically, we have now written our first own, or you could write this if you, in half an hour of coding, you could write your first own simple probability-based machine learning algorithm classifier. And let's do that very quickly. We have let's take 10 minutes and really calculate this by hand so that you get a good feeling for how this works. So first of all, take a piece of paper or note, mental note, and come up with 5 words that describe the course intelligent systems, and 5 words that calculate that describe the course web technology. So we have intelligent systems and web technology. And then we are going to take some person who will give us their 5 words, and we should predict whether they are talking about intelligent systems or talking about web technology. And of course, what do we have to do first before we can start with that? We have to separate into a training set and a testing set. So I would suggest it's not 40% down here, but let's take this group as our testing set, and all the rest is the training set. Yeah. So if we train, when we train our probability, you're not allowed to raise your finger. Okay. 5 words for web technology and 5 words for intelligent systems. Okay, let's collect some words and then count how often they occur in the description. So what words do we have for intelligent systems?
Artificial.
Okay, do we have anything for web technology? Yeah. Forms. Forms. Yeah.
No, phones.
Phones. Yeah.
F-O-N-Z-S.
He showed me a phone. I'm sure he wanted to say phone. Yeah. Anything else?
CSS.
Huh? CSS. Okay. Board is full. We now have a set of features, and so these now give us probabilities, because now I think I guess that in previous years the distinction was not that clear between the two. So I guess that is, who of you is How many of you had artificial in your description of IS? One, two, three, four, let's say 10. How many of you had the word artificial in your WT? Yeah, I was afraid that would happen. Agent, probably similar. 8. Yeah, I think we can go on. We've managed to get a perfect overlap, a perfect predictor.
Next time do artificial intelligence and machine learning, then you get more overlap.
Yeah, so I'm surprised why this happened, because it never happened before. So what? Maybe I gave some more hints, or I was less free in my. So you know what we do? We're cheating. So I think I had something else last time. I don't understand why that doesn't work. So let's suppose there were 2 strange people who thought that this artificial would occur in web technology. It's obviously not intelligent. So we had logic, I think, would occur in several. I'm confused now because I'm sure this didn't happen last time. Yeah, you see the principle. Why phones, by the way? Who had phones?
We had an assignment. The project last year was based like on a web page selling phones.
Okay, but still, how many of you had in their list of for web technology had phones? I thought so. How many of you have? Oh, sorry. How many of you have phones in intelligent systems? I know the answer. Okay. So this is a bit weird, but yeah. Yeah.
You only have 4 lightweight for technology cohorts, and you also do just add Internet of Technology.
Yeah, I have something to improve for next year. I need to think carefully about this example where there's more ambiguity. I think it's very clear here. So the classifier should now really work properly if we do it correctly. Because what we now have to do is and I even did it wrong, because I should have given each of you the choice of doing either web technology or intelligent system. So this really is a sort of the wrong approach. Huh? Should start over? Okay. We still have enough time for me to start over. So let's start over. So can each of you choose a description for the course Intelligent Systems? What else did you say?
Search.
Yeah, but we need a course that's closer to intelligent systems. What do we have in logic and sense? That's a good one, yeah. Okay. So each of you chooses now either intelligent systems or logic and sets. Yeah? We're going there. Okay? And think of 5 words. Okay, so give me some words. So I come up with logic, chess, propositions, one-upson, anything else? Agent? Okay, that's good enough. I think that's good enough. So, how many of you have chosen to model web technology? No, sorry, we didn't have web technology. Intelligent systems. I'm not very popular. So that's 6, 7, 8. How many of you have chosen web logic and sets? It's not popular either, so we have 7. And we have also a third class, which we sort of have to think of what it means. Okay, so how many of you, if you have an intelligent systems decision, how many of you have used the term logic? So that's 4. How many of you who have a logic and sets? That's 2, 3, 4, 5, there. Chess, who's had chess on the list? 1 person, very good. And I guess nobody here. Propositions, 2, 3. Oh no, that should be logic and sets. 5, 6. Schnapsen, 7. I got more than the 8 there, so I need to keep it a bit. I guess this is a nil. Agents, 1, 2, 3, 4, 5. And this is a 0 again. Okay, so now we have a set of 15 people who voted. And now we can basically, for each of the features, we have made this table, filled in now. How often do in the class, yes, do we count the word logic and so forth? Yeah? And based on this data, we can now calculate all the things we need for our estimation for the Bayesian network. Yeah? For our naive Bayes classifier. Because we do now the probability of intelligent systems. What is the probability of intelligent systems? That someone haven't chosen intelligent systems. What is the probability of this? Come on, I have to leave. Not big. Huh? 8 over 50, yes. And the other one, of course, 7 over 50. Yeah? What is the probability? Now, what are the conditional probabilities of a certain word to happen? So what do we need to calculate is here the probability of the word logic occurring in the case of one of those 2 classes. So let's do the probability of the word logic. Given now we have yes. Anybody? Yeah? So we have eight people with an IS, and we have 4, so 4 over 8. Yeah? So I have to classify your reaction now, either it's too simple, or it's too chaotic, or it's too difficult. And I'm not sure what the answer is. But this is really easy. Yeah? You just have to take your word, how often does it occur in a certain class, and calculate how often does it occur how often does the word occur in those 7, 8 documents. Yeah? And then we can calculate all of those probabilities, apart from one of them, or we can calculate it, but we get a problem. Namely, what is the probability of the word agent occurring in our estimation in logic and sets? In logic and sets, this one. 0. Yeah. So what's then our value for with our naive Bayesian classifier? What is the estimation if agent this is 0? Then our calculation of our rule. Well, I think I have it here as well. So this is then the calculation we do. We maximize over all the words we have, and we just calculate the prior probability of IS being the case. So that is this one. We have the 8 over 15. And we multiply it with all the values of a certain word occurring and the class you want to classify in. So that's 4 over 8 in this case. And we do that for all the words in our document. Problem is that if we have a 0, this value gets automatically 0. And as we have in our table zeros here, we will have a 0 prediction. And we will probably would also have a 0 prediction here. So what you usually do in naive Bayesian learning is that you assign not the value 0 to this, but you assume that there would be some examples if you had a huge data set, and you just apply some adjustment and give it a very small value. This is called Laplace smoothing. And the smoothing basically helps you to avoid too small probabilities here. And all in all, you just have to sort of naively calculate the number of occurrences of these words in the documents, calculate the probabilities of the class itself, and the probability of a word occurring in one of those documents from this class, and multiply the values, and you get your estimation. And then you take the bigger one, and that gives you your class to classify into. Yeah? So this has a number of assumptions, namely that you have the conditional independence of the features, you do the smoothing, and these were the two assumptions. Still, it works very often as a good estimator. So what you can basically see is that you might have a correct estimation. If you have a correct estimation, then you might get an accurate prediction. But in this case, we have a pretty accurate prediction in many cases, but it's absolutely no probability that we get out. So it's an estimation, it's an approximation of some probability values. But the nice thing about it is that it's really a very, very powerful and relatively good machine learning algorithm that you could implement in an hour just by collecting the data, counting the data, running through an array of values here, and if you write it down in a correct way, you will get a prediction very, very easily, which usually works pretty well. Interestingly, this approach doesn't give you a linear classifier, but it, in a way, it sort of gives you your probability distribution over your space, your feature space, in terms of something being closer to one value than another, and then basically wherever the valley is of your values, there is also your classification line. So practice this algorithm is just sort of good to have an hands-on experience. And it really isn't very difficult or deep to do, yeah.
We want to learn more about public philosophy, so I can come up with a place.
No, there isn't. That would go too much into depth. So I cannot tell you much more than this idea of you assign some small value. There should be in the book. There should be more discussion about it. I don't have much more to say here. Yeah. So I will start with the games and tomorrow. So we leave that for today. Let's just stop here and see you tomorrow, everybody.